Usually when we talk about writing code, there is this expectation of magic.
Oh, absolutely.
I mean, you type some human-readable words like, if or while or print. You hit a button and suddenly your computer is just doing something incredible.
Right, it's rendering a massive 3D world, or calculating the trajectory of a spacecraft, or, well, just sending an email.
Yeah, exactly. We just sort of expect the machine to understand us. But have you ever stopped to wonder how a computer actually reads the code you write?
It's a fascinating question, really.
Because how does a machine, which, I mean, fundamentally only understands electricity and silicon, right? Just voltage gates opening and closing. How does it turn a raw text file into a functioning application?
Well, it is a massive gap to bridge. It feels completely seamless to the programmer sitting at the keyboard. But underneath that run button is one of the most complex translation processes ever engineered.
It's wild to think about.
It is. We are talking about taking abstract human expression and literally distilling it into raw, executable machine mechanics.
And that translation process happens inside something called a compiler. So today, we are acting as your proxy for a deep dive masterclass in compiler construction.
Yes, specifically looking at the architecture and formal language theory designed by Dr. E.O Bennett and Dr. E.E Omaegbu at Rivers State University.
Right. We have been poring over their lecture notes, and we are going to extract the absolute core of how a machine learns to read.
And we are focusing heavily on the very first phase of this translation, a process called lexical analysis, but we'll also touch on syntax analysis and set theory, which are totally crucial.
Okay, let's unpack this, because lexical analysis is really the front door of the compiler, right?
Exactly. To understand this, you really have to realize that when you feed a text file into a computer, it doesn't see words or equations like we do.
It just sees a void of characters, right?
Pretty much, it sees a completely flat, unorganized stream of individual characters. It sees an I, then an F, then a space, then a bracket.
So it's just a giant string of letters and symbols.
Right. And lexical analysis is the system that acts as the first line of defense. Its primary job is to take that raw input string and convert it into a sequence of meaningful symbols.
Which in the field we call lexical tokens, or just tokens.
Precisely. It is playing a game of grouping.
So if I hand you the individual letters C, A, and T, you don't just see 3 isolated letters.
No, your brain instantly groups them and says, oh, that is the concept of a cat.
Right. But a lexical analyzer, or a lexer as it's commonly called, is doing quite a bit more than just grouping characters, isn't it?
Oh, yeah, much more. It also acts as the ultimate editor, really just cleaning up the absolute mess that programmers tend to leave behind.
A mess is definitely the right word for my code.
Well, a huge part of its job revolves around secondary tasks.
Mm-hmm.
For instance, it eliminates every single comment in the code.
Wow.
Yeah, and it strips out all the white space. I mean, every blank, every tab, every single new line character.
Wait, really? It just deletes all the formatting?
Completely deletes it.
Because, I mean, programmers spend hours, right, like arguing over tabs versus spaces, formatting their code so it looks perfectly readable on the screen.
And the computer could not care less about any of it.
That is kind of hilarious.
It is. The machine does not need your paragraph-long explanation of why a certain variable exists. And it certainly doesn't care about your beautiful cascading indentation.
So to the machine, all of that human-centric formatting is just noise.
Exactly, just noise. The lexer strips that noise away, so the rest of the compiler only receives pure executable logic.
Okay, but if it is deleting all the new lines and formatting, how does it handle errors?
What do you mean?
Well, if I write 1,000 lines of code, right, and I miss a semicolon on line 402, the compiler usually yells at me and says, error on line 402.
Right.
But if the lexer just deleted all the line breaks to create a flat stream of tokens, how does the system even know we are on line 402?
That is a crucial secondary task of the lexer. It performs error correlation. As it is scanning through that raw text and throwing away those new line characters, it is silently keeping a tally. It tracks the line numbers internally.
Oh, I see.
So this way, if the deeper, more complex parts of the compiler encounter a fatal logic error later on, they can ask the lexer, hey, where did this token originally come from?
And the lexer can map the machine's internal state directly back to the human-readable line in your text file.
Exactly. It maintains the map between the human world and the machine world.
That makes a lot of sense. But here's something I don't quite understand about the architecture.
Yeah.
The lexer is just the first step. The next major phase of the compiler is called the parser, right?
Yes, the parser.
Which is the system that actually figures out the grammar and the logic of the code. Now, the documentation describes the lexical analyzer as acting like a subroutine to the parser.
Correct.
So the parser basically wakes up, calls the lexer, and says, hey, give me the next token.
Yep, that's the standard flow.
Why not just merge these two? I mean, why wouldn't the parser just read the text file, ignore the spaces, and figure out the grammar all in one single fluid motion?
Well, it really comes down to software engineering architecture. If you merge them, you create a monolithic system that is, frankly, incredibly difficult to build, maintain, and optimize.
So it's just too messy.
Exactly. Splitting them up, separating the lexical analyzer from the parser, is a classic design pattern. This is especially relevant for anyone approaching this from a software engineering background.
Right, which the academic materials frame as the embauche-noir context for understanding systems design.
Exactly. And there are 4 distinct, highly practical reasons for this separation of concerns. The first is simply the simplification of the design itself.
I can see how doing one thing at a time is conceptually simpler, sure. But isn't managing 2 separate software modules more complicated than just having one loop that reads and parses simultaneously?
Not when you consider the physical realities of computer hardware. And this actually leads directly into the second reason, which is isolating input and output issues.
Okay, I/O issues.
Yeah. Reading a physical file from a hard drive or a solid-state drive, character by character, is an incredibly messy, slow, and unpredictable process.
Because it's dealing with the actual physical hardware.
Right. You're dealing with hardware buffers, you are dealing with end-of-file markers, operating system interrupts. It's a lot.
Oh, wow.
So if you build a parser that is trying to deduce the high-level complex grammar of a programming language, you absolutely do not want that elegant grammatical logic tangled up with the messy physics of reading bits off a disk.
That makes total sense. By separating them, you quarantine all the ugly I/O logic strictly inside the lexical analyzer.
Exactly. You keep the messy, real-world physics of the hard drive away from the pure, abstract math of the parser.
Okay, so that's 2. What is the third reason?
The third reason is that it creates a drastically smaller, much faster parser. We call this slimming the grammar.
Slimming the grammar.
Yeah, because the lexer has already stripped out every comment, every blank space, and every new line. The parser never even has to evaluate them.
Oh, I see. Because if the parser had to constantly check, like, is this a space? No. Is this a comment? No. Is this a variable? It would just slow to a crawl.
It would be agonizingly slow. By feeding the parser a concentrated, purified stream of meaningful tokens, you drastically reduce the sheer number of rules the parser has to process.
It is exactly like prep work in a professional kitchen.
Oh, I like that analogy.
Yeah. The lexer is the sous chef who washes, peels, and chops all the vegetables. And the parser is the head chef.
Right, and the head chef doesn't want to look at potato peels or dirt.
Exactly. They just want a perfectly portioned bowl of ingredients so they can focus entirely on combining them into a complex dish.
That's spot on. The sous chef does the tedious mechanical work so the head chef can execute the complex logic.
Love it. So what's the fourth reason?
The fourth reason brings us to the mathematical foundation of how computers operate. It essentially comes down to computational efficiency.
Okay, math time.
The lexer and the parser actually use 2 entirely different mathematical models to do their jobs. The lexers are built on a model called finite automata, which is incredibly lightweight, requires almost 0 memory overhead, and runs blindingly fast.
Finite automata. Got it. And the parser.
The parser, however, has to understand nested structures, right?
Oh.
Like loops inside of loops or parentheses inside of parentheses.
Right.
To do that, it requires a much heavier model called a push-down automaton.
Now, we are definitely going to need to dig into what a push-down automaton is later, but I'm assuming the push-down part implies a lot of heavy lifting.
Oh, it does. It implies memory management, specifically using memory stacks.
Okay.
If you forced the parser to read every single raw character using its heavy-duty, memory-intensive push-down automaton, compiling a simple program could take minutes instead of milliseconds.
Oh, wow. So offloading the character-by-character reading to the hyper-efficient finite automata of the lexer ensures the whole system runs at optimal speed. Okay, so we have the sous chef separated from the head chef for speed, cleanliness, and hardware isolation. Let's look closely at what the sous chef is actually putting in the bowl.
Let's do it.
The core of lexical analysis revolves around three specific concepts. And apparently, based on the notes, these are the three most universally confused concepts in compiler theory.
Oh, absolutely. Students constantly mix them up.
They are tokens, patterns, and lexemes.
Yes, the holy trinity of lexical analysis. If you don't have a razor-sharp distinction between these three terms, the rest of compiler theory will just sound like complete noise to you.
Well, let's break them down then, starting with the token.
Okay, a token is a categorized unit of the source text. It is an abstract category.
Abstract category.
Right. Examples of a token would be the concept of a keyword, an identifier, an operator, or a constant. When the parser is trying to figure out the grammar later on, it only looks at tokens.
So the token is basically just the label on the box.
Exactly.
Okay, so what is a pattern?
The pattern is the formal rule that dictates what is allowed to go inside that box.
The rule.
Yes. It is the exact specification, usually written out as a mathematical regular expression, that describes the set of strings associated with a particular token.
So it is the blueprint the lexer uses to test the text it reads.
That's a great way to put it. It's the blueprint.
Which leaves the lexeme.
Right. The lexeme
Yeah.
is the actual physical sequence of characters in your raw source code that successfully matched the pattern and formed a specific instance of a token. It is the raw data itself.
Okay, let's try to ground this because I want to make sure the relationship between these three is perfectly clear.
Sure, go ahead.
Imagine a massive mail sorting facility, okay? The token is the concept of a zip code. That is the category of information the post office cares about.
Right.
The pattern is the strict rule. It must be exactly 5 consecutive numeric digits. That's the blueprint. And the lexeme is the literal, physical black ink scratched onto a specific envelope that reads 90210. The ink is the lexeme, the rule is the pattern, the category is the token.
That works perfectly. The ink on the paper is your lexeme. Let's actually apply that directly to a programming example.
Okay.
Let's take the token category called relation, meaning a relational operator used to compare two things, like checking if one number is smaller than another.
So the token is relation.
Correct. For that token, the pattern is a strict rule that says the string of characters must be exactly one of the following sequences: less than or equal to or greater than or equal to or greater than or not equal to.
So that specific list of options is the pattern.
Exactly. The lexemes then are the actual symbols the lexer encounters in the text file.
Right.
So if you typed, if x is less than or equal to y, the specific characters for less than or equal to that the lexer reads, that forms the lexeme. It matches the pattern, so it outputs the token relation.
Okay, that makes sense. How about numbers?
Well, for a token called num, short for a number, the pattern is a regular expression defining any valid numeric constant. So maybe a string of digits, potentially including a decimal point.
Yep.
The lexemes would be the actual numbers you typed, like 3.1426 or 0 or 100. Those actual characters are the lexemes.
Got it. And what if I create a variable? Let's say I name a variable player score.
In that case, the token category is id, short for identifier.
Okay.
The pattern is a rule that generally states the sequence must start with a letter and can be followed by any combination of letters and digits.
Right.
And the lexeme is the exact string of characters,
Yeah.
PLAYERSCORE.
Okay, wait. I see a massive problem here.
What's that?
If the parser only sees the tokens, we have an issue. Let's say I write a program with 2 variables. One is player score and the other is enemy health.
Right.
The lexer reads player score, applies the pattern, and spits out the token id. Then it reads enemy health, applies the pattern, and spits out the token id. It hands 2 identical id tokens to the parser. How on earth does the parser know which variable is which? Didn't we just destroy the actual lexeme data by categorizing it?
You have just hit on the exact reason why a simple token stream isn't enough. The parser absolutely needs to know the difference between player score and enemy health.
Yeah, or the game is going to be very weird.
Exactly. So to solve this, a token isn't just a single label. It is often passed as a pair of values. It contains the token category and an attribute.
An attribute.
Yes, and in almost all modern compilers, that attribute is a highly specific memory pointer that directs the parser to a data structure called the symbol table.
The symbol table. Okay, this sounds like the master ledger of the whole operation.
It is exactly that. It is a shared, dynamically updated database used by almost every phase of the compiler.
So how does the lexer interact with it?
When the Lexical Analyzer finds a lexeme that fits the id pattern, like player score, it doesn't just throw those characters in the trash after categorizing them.
Thank goodness.
Right. It actively creates a brand new row in the symbol table. It stores the exact string player score in that row, along with the line number it was found on, and it leaves room for the parser to later add information about what type of data it holds.
Oh, that's incredibly clever.
Yeah, and then the Lexer constructs the token. It hands the parser the category "aid" plus a precise memory address pointing directly to that new row in the symbol table.
So it passes a coordinate. It tells the parser, hey, I found a variable. If you want to know its exact name and details, go look at row 42 in the ledger.
Exactly.
Let's actually walk through a complete statement to see this in action. The classic physics equation from the Fortran days.
Yeah.
EE equals MC2.
The old, reliable.
Yeah. How does the Lexer chew through that?
Let's track it character by character. The Lexer reads the letter E. It checks its patterns and sees this matches an identifier.
Okay.
It creates an entry for E in the symbol table. Then it outputs the pair token, .ed, and a pointer to the symbol table for E.
Next is the equal sign.
It reads the equal sign. It matches the pattern for an assignment operator. It outputs the token, assign op. Now, notice something critical here.
What's that?
There is no pointer attribute attached to this token.
Because an equal sign is just an equals sign?
Right.
There is no unique flavor of equals. The parser doesn't need to look up any extra details in a ledger to know what to do with it.
Exactly. The token category itself contains 100% of the required information.
Okay, so then it reads a letter M.
Same process as before. It generates Z and a pointer to the symbol table for M. Then it reads the multiplication star, which generates multi-op, again with no pointer.
Then the C, it generates id and a pointer to the symbol table for C.
Then it encounters the two stars, which in Fortran is the power operator. It outputs power op.
Right.
And finally, it reads the digit 2. It matches the number pattern, places the value in the symbol table or directly in the attribute, and outputs num with the integer value 2.
It is an incredibly elegant compression algorithm, really.
It really is.
It takes raw human text and compresses it into this rigorous mathematical stream of coordinates and categories without losing a single drop of the original context.
And it does it so fast.
But this all relies on the Lexer perfectly understanding these patterns. And a pattern isn't just a vibe, right? It has to be a hard-coded mathematical rule.
Right. Machines don't do vibes.
Exactly. So if I'm building a compiler, how do I write rules that are rigid enough for a machine, but flexible enough to catch every possible variable name a human might dream up?
To answer that, we have to leave the realm of practical software engineering for a moment and dive into theoretical mathematics.
Oh boy.
Specifically, set theory and formal language theory. You really cannot design the rules for a lexical analyzer without understanding the absolute mathematical boundaries of what a machine can and cannot compute.
So where do we start with that?
Well, to solve this, computer scientists actually borrowed a concept from linguistics called the Chomsky Hierarchy.
Named after Noam Chomsky, the linguist.
Yes. In the 1950s, Chomsky developed a way to classify formal languages based on their generative power.
Generative power. What does that mean?
Basically, how complex the rules need to be to generate or recognize the sentences of that language. He created a hierarchy from type 0 down to type 3.
Okay.
But before we can look at the hierarchy itself, we really need to establish the foundational set theory vocabulary that the architecture relies on.
Right. So if you haven't taken a discrete math class recently, just bear with us, because understanding this is the key to understanding how a computer thinks about text.
Absolutely.
So the very first building block in the theory is the concept of an alphabet, which is mathematically represented by the Greek letter sigma.
Right. An alphabet, sigma, is simply a finite set of symbols.
A finite set.
Yes. In the context of our computer, sigma is usually the standard set of ASCII characters. It is the finite list of keys on your keyboard.
Yeah.
A, B, C, 1, 2, 3, plus, minus, open parenthesis, and so on. It is a strictly limited finite set.
Okay, that's easy enough to grasp.
Now, the magic happens when you start combining those symbols. The theory introduces the concept of sigma star.
Sigma star.
Sigma star is the mathematical set of all possible strings that can be generated by combining the symbols in your alphabet of any possible length.
Any length.
Any length. It even includes the empty string, which is literally a string of length 0.
Okay, let me visualize this.
Okay.
If my entire alphabet consisted of just two symbols, right? The letter A and the letter B.
Right.
Then sigma star would include A, B, A, B, 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 A, and it would just keep going forever.
It goes on to infinity. Sigma star is what mathematicians call countably infinite. There is absolutely no end to the number of permutations you can create.
Mind-boggling.
It is. Now, here is the most important definition in the entire theory. A language is simply any subset of sigma star.
Okay, wait.
A language is just a specific collection of strings pulled out of that infinite pool.
But if the pool of strings is infinite, that means there are an uncountable number of possible languages you could invent.
Exactly. And that is the core engineering problem. A computer only has a finite amount of memory.
Right.
We cannot give a computer an infinite list of valid strings and say, hey, check if the user's code is on this list. It would run out of memory instantly.
So what do we do?
We have to provide the computer with a finite representation, a rule book, that allows it to dynamically recognize whether a string belongs to a specific language or not.
And the Chomsky hierarchy categorizes the different types of rule books we can write based on how much computational horsepower they require.
Precisely.
Let's look at the hierarchy, starting at the bottom with the most restrictive, simplest rules. Type 3 languages.
Type 3 languages are known as regular languages. Mathematically, they are the weakest and simplest.
Weakest in what way?
Well, a language is regular if it can be perfectly described by a regular expression and recognized by a finite state automaton.
Okay, give me an example.
The documentation provides a classic mathematical example. Let's define a language called L1. L1 consists of strings that have some number of A's followed by some number of B's.
Okay.
Mathematically, it is written as A to the power of M, B to the power of N, where M and N are greater than 0.
So valid strings in L1 would be A, B, A, B, 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 as long as it's a block of A's followed by a block of B's if it's the rule.
Correct. And this type 3 regular language is exactly the mathematical domain in which lexical analysis operates.
Really?
Yes. Every single pattern we discussed earlier, the rule for finding an identifier, the rule for finding a floating point number, the rule for relational operators,
Yeah.
every single one of them can be mathematically expressed as a type 3 regular language.
But if they're the weakest mathematical language, they must have a catch. I mean, what can't they do?
The fatal flaw of a regular language is that it possesses absolutely zero memory.
Zero memory.
None. It cannot count to an arbitrary number, and it cannot remember what it saw 3 steps ago. Because it has no memory, a regular language cannot check if things are balanced.
Give me an example of what you mean by balanced.
Parentheses. In programming, if you open 3 parentheses, you must close exactly 3 parentheses. A regular language physically cannot evaluate that. It cannot say, I just saw 3 open parentheses, so I must store the number 3 in my memory and then count down as I see the closing parentheses. It has nowhere to store the number 3.
But balancing parentheses and brackets is the entire structural foundation of writing code.
It is.
I mean, every function, every loop, every array relies on nested, balanced structures. If the lexical analyzer is mathematically incapable of understanding balanced parentheses, how does the compiler ever work?
Because the lexical analyzer doesn't need to understand them, it just categorizes them.
Oh, I see.
It sees an open parentheses, says here's an open parenthesis token, and moves on. To actually understand the nested structure, the tokens are handed to the parser.
Right, the parser.
And the parser operates one level higher on the Chomsky hierarchy. The parser uses type 2 languages, which are called context-free languages.
What makes type 2 different from type 3?
Context-free languages are generated by context-free grammars and are recognized by a much more powerful machine called a push-down automaton.
Okay, you mentioned push-down automata earlier.
Right. The crucial difference is that a push-down automaton possesses a memory stack. Let's look at the type 2 example from the text.
Okay.
Language L2 is defined as exactly n A's followed by exactly n B's. A to the power of n, B to the power of n.
So strings like Abe, 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 the number of A's and B's must be perfectly symmetrical.
Yes. To recognize this, the machine must count the A's. A push-down automaton does this by physically pushing a token onto a memory stack every time it sees an A.
Okay, so like a stack of plates.
Exactly. If it sees 3 A's, the stack has 3 items piled up. Then when it starts seeing B's, it pops 1 item off the stack for every B.
Oh, that's so smart.
Yeah. If the string ends and the stack is perfectly empty, the machine knows it was perfectly balanced.
This is a massive light bulb moment. The Lexer is incredibly fast because it uses simple, memoryless type 3 math just to chop the text into categorized chunks. Then it hands those chunks to the parser, which uses the heavier memory-enabled type 2 math to actually check the grammatical balance of the program.
You've got it perfectly.
But wait, let's go a bit deeper into this syntax analysis part, because the focus of our deep dive specifically includes grammar rules and how to present a derivation as a parse tree.
Oh, absolutely. The parse tree is the ultimate output of the parser.
So the Lexer gives the parser these tokens, what does the parser actually do with them using those context-free grammars?
It performs syntax analysis by trying to build a tree structure out of the tokens.
The tree structure.
Yeah.
Yeah.
Think of a grammar rule, kind of like a sentence structure in English.
Okay.
A sentence is made up of a noun phrase plus a verb phrase.
Right, like the dog ran. The dog is the noun phrase. Ran is the verb phrase.
Exactly. In a compiler, the grammar rules dictate how tokens can be combined into larger structural elements, like expressions or statements. The parser takes the linear stream of tokens and attempts to derive the overall structure by applying these rules backwards, basically. This process of derivation is visualized as a parse tree.
Okay, so paint a picture of this parse tree for me. What does it look like?
Well, picture an upside-down tree. The very top point is called the root node, and it represents the entire program or the entire statement.
Okay, the root is at the top.
Right. Then it branches downwards. The interior nodes, the branches, represent the non-terminal symbols, basically the grammar rules themselves, like assignment statement or math expression.
And what's at the very bottom?
At the very bottom are the leaves of the tree. The leaves are exactly the terminal symbols. In other words, the leaves are the tokens that the lexer gave us.
Oh, wow. So the tokens are the literal leaves of the syntax tree.
Exactly. Let's go back to our Fortran example, E equals C2.
Okay.
The root node might be labeled assignment statement.
Right.
That root node branches into 3 children. The left side, the equal sign, on the right side.
Okay, so the left child is just the token for E. That's a leaf.
Yes. The middle child is the token for the equal sign, also a leaf.
And the right side?
The right side is a non-terminal node called expression, because MC2 is a complex math expression.
Oh, I see. So that expression node has to branch further down.
Exactly. It branches into M, the multiplication operator, and another sub-expression for C2, which branches further into C, the power operator, and 2.
So the parser is essentially drawing lines connecting all these isolated tokens into a strict logical hierarchy.
That is syntax analysis in a nutshell. If the parser can successfully build a valid tree where all the leaves match the tokens in the exact order they appeared, then the code is grammatically correct. If it can't build a tree without breaking a grammar rule, it throws a syntax error.
That is incredible. It really highlights why the two phases have to be separate. The lexer is just tossing leaves into a pile, and the parser is the one meticulously taping them onto branches to see if they form a proper tree.
That is a very poetic but very accurate way to look at it.
So we know we want to use a type 3 regular language for our lexer because it is fast and requires no memory stack. But a regular language is just an abstract mathematical concept. It is just theory on a chalkboard.
Right.
If I am an engineer, how do I actually build a machine to process that theory? How does the lexer physically navigate these rules?
This is where the theory takes physical shape. A regular language is recognized by a computational model called a finite state automaton, or an FSA.
Okay, an FSA?
You can visualize an FSA as a highly structured flowchart. It consists of circles, which represent states, and arrows connecting those circles, which represent transitions.
Circles and arrows?
Yeah, the machine always begins in a designated starting state. It reads exactly one character of input, looks for an arrow matching that character, and follows it to the next state.
Okay.
Then reads the next character, follows the next arrow, and so on.
And how does it know if the string actually matched the pattern?
Well, certain states in the flowchart are designated with a double circle. These are called accepting states.
Accepting state.
Right. If the machine reads the entire string of text, and when the text runs out, it happens to be sitting on an accepting state, the machine outputs true. The string is accepted.
And if it's not?
If it runs out of text and it is not on an accepting state, or if it reads a character and there's no arrow for it to follow, it outputs false. The string is rejected.
That sounds incredibly simple.
It is, conceptually.
But wait, there is a fundamental flaw there if we are trying to use this for a lexer.
Hmm.
You said the FSA reads the entire string of text and then says true or false.
I did.
If I feed my compiler a source code file with 10,000 lines of code, the lexer's job isn't to say, true, this entire file is one giant valid token. Its job is to chop the file up into thousands of individual tokens.
You have just identified a major conceptual hurdle that the academic materials specifically flag as a common point of confusion for students.
Really?
Yes. An FSA in its purest, most rigorous mathematical form strictly accepts or rejects a complete isolated string. It is a binary yes-no machine. Because a compiler needs to process a continuous, massive stream of text and chop it into pieces, practical lexical analyzers do not use pure FSAs. They use an engineered variant called a transition diagram, or a TD.
Okay, so how does a transition diagram alter the rules of the Flowchart.
The mechanics of moving from state to state are identical. The critical difference is what happens when the machine reaches the end of a token.
Because an FSA just returns a Boolean true or false, right?
Exactly. A transition diagram, however, is designed to read characters until it identifies a complete token, at which point it abruptly halts, returns that specific token to the parser, and crucially, it resets its internal state and prepares the input buffer to begin searching for the next token, starting from the exact character where it left off.
Oh, that makes so much sense.
Yeah, in a practical transition diagram, accepting states usually don't have any outgoing arrows. Hitting an accepting state is the signal to pack up the token, ship it out, and restart the process.
Okay, so the transition diagram is the engine. The documentation breaks the lexical analyzer down into two distinct substages that run this engine: the scanner and the evaluator.
Yes, the scanner is the part of the software that is directly executing the logic of the transition diagram. It is entirely mechanical.
Mechanical how?
Its only job is to blindly follow the arrows based on the characters it reads. It moves from state to state until one of two conditions is met.
What's the first condition?
The first condition is that it lands on an accepting state. It says, great, I found a valid lexem, it notes the category, and it stops.
Okay, and the second?
The second condition is that it lands in what the architecture calls a dead state.
A dead state? That sounds like a fatal crash. What triggers a dead state?
A dead state is simply a non-accepting state that has absolutely no valid outward transitions. It is a dead end in the maze.
Oh, I see.
When the scanner hits a dead state, it realizes, based on the character I just read, it is mathematically impossible for me to ever reach an accepting state no matter what characters come next. So it stops the scan.
But it doesn't crash.
No, it doesn't crash. It looks backward in its short-term memory to find the last valid accepting state it passed through during this run.
Oh, clever.
Yeah, it uses that previous state to define the token, and any extra characters it read before hitting the dead end are pushed back into the unread input stream.
It's like walking down a hallway, realizing the door at the end is bricked over, and walking back to the last open door you passed.
That's a perfect way to visualize it.
So that is the scanner. What does the evaluator do?
Once the scanner has successfully isolated the boundaries of the lexem and identified its abstract category, it passes the raw text to the evaluator. The evaluator's job is to actually process the literal characters and compute their meaningful value.
Okay, give me an example.
Let's say the scanner isolates the string 123 and tags it as a number. The scanner doesn't know what 123 means, it just knows it fits the numeric pattern. Right. The evaluator takes the ASCII character 1, the character 2, and the character 3, performs the necessary arithmetic, and converts them into the actual binary integer representation of 123.
Oh, okay. So it's doing the actual translation into a value.
Exactly. It pairs that computed value with the category to form the final token.
Wait, earlier we talked about the lexer deleting whitespace and stripping out comments. Is that the scanner's job or the evaluator's job?
It is the evaluator's job.
Yeah.
This is one of its hidden superpowers.
How does it do it?
Well, if the scanner isolates a massive block of text and identifies it as a comment, it hands it to the evaluator. The evaluator looks at the category, sees it's a comment, and simply returns a null value.
It just drops it.
It drops the token on the floor. It acts as a filter, entirely suppressing the comments so the parser never even knows it existed.
That is so efficient. Let's make this abstract transition diagram incredibly concrete.
All right.
Picture a flowchart in your mind. The documentation provides an excellent practical example, labeled TD Example 2.
I know the one.
This specific diagram is designed to recognize three things: an unsigned integer, the standard addition operator, which is a single plus sign, and the increment operator, which is two plus signs together.
Okay.
Let's walk through the flowchart. We turn the machine on, and we are sitting in state 0.
At state 0, the machine is idling, waiting for input. The text file feeds it its first character. Let's say the character is a single plus sign.
Okay.
We look at the arrows leaving state 0. There is an arrow labeled with a plus sign that points to state 1. So the machine transitions to state 1.
Okay, we are in state 1. We've read 1 plus sign.
Now it needs the next character to know how to proceed. Let's say the next character is another plus sign.
Right, so we have plus plus.
We look at the arrows leaving state 1. There is an arrow labeled with a plus sign that points to state 3. State 3 is an intermediate node that immediately forwards the machine to state 5.
And state 5.
State 5 is a double-circled accepting state. The scanner halts. It recognizes that it has found the INCR token, representing the plus plus increment operator. It returns the token and resets.
Okay, that is the happy path. That's easy. But here is where the mechanics get really tricky.
Yeah, edge cases.
What if the code wasn't plus plus? What if the programmer wrote +5? We start at state 0, we read the first plus sign, we move to state 1. But the next character fed to the machine isn't a plus, it is the digit 5. What does the machine do?
This scenario exposes the true genius of the transition diagram. The machine is sitting in state 1. It reads the digit 5.
Right.
It looks at the arrows leaving state 1. There is an arrow designated for any digit or any letter or basically anything that isn't a plus sign.
Oh, another arrow.
Exactly. That arrow points to state 2. The machine transitions to state 2. And state 2 happens to be an accepting state for the ADD token, representing a single addition operator.
But hold on, this seems like a catastrophic bug.
Why is that?
Because the machine was sitting in state 1, it had to physically consume and read the digit 5 just to trigger the transition to state 2.
Right.
So it ate the 5 to prove that the plus sign was just a plus sign. If it stops now and returns the ADD token, hasn't it completely destroyed the digit 5?
You would think so.
The parser is going to think the code was just a plus sign and the number 5 will just vanish into thin air.
You've zeroed in on one of the most critical mechanical challenges in all of compiler design. The machine overshot its target.
Overshot it.
Yes. It had to read into the future to resolve an ambiguity in the present. To solve this, the architecture introduces a crucial memory management concept called retraction.
Retraction.
If you look closely at the transition diagram in the notes, state 2 has a special marking next to it. It is marked with an asterisk.
What does the asterisk command the machine to do?
The asterisk is a hard-coded instruction that triggers a retraction. When the machine reaches state 2 and realizes it needs to output an ADD token, the asterisk tells the input buffer, hey, that last character I just read to get here, the digit 5, I didn't actually want it. Take it back.
Take it back.
Yes. It physically forces the memory pointer to roll backward one space, pushing the 5 back into the unread input stream.
Oh, wow.
This guarantees that when the Lexer resets and begins scanning for the very next token, the 5 is sitting exactly where it should be, ready to be correctly processed as the start of a number.
It is exactly like reading a poorly structured sentence in a novel.
How do you mean?
You are reading along, taking in words, and suddenly the context of the sentence shifts.
No.
You realize the word you read 2 seconds ago meant something entirely different than what you assumed.
Oh, I hate when that happens.
Right. And what happens physically? Your eyes stop, they dart backward across the page. You retract your gaze, and you reread the sequence with the newly acquired context.
That is a phenomenal analogy.
The Lexical Analyzer is doing the exact same thing on a microscale. It peers into the future to resolve ambiguity, and if it realizes it went too far, it physically yanks its reading pointer backward.
It is exactly a retracted gaze. But implementing this retracting gaze inside a computer's memory architecture is remarkably difficult.
I can imagine.
We established earlier that reading a file characters by character from a hard drive using individual system interrupts is devastatingly slow.
Right.
If every single time the Lexer wanted to look ahead one character, it had to ask the hard drive, and then every time it retracted, it had to tell the hard drive to rewind. The overhead would be astronomical.
So how do you manage the memory pointer so it can dart back and forth at lightning speed without talking to the hard drive constantly?
You build a localized, highly optimized staging area in the computer's RAM. The standard architecture for this is called the 2-half buffer design.
2-half buffer, okay.
Instead of asking the disk for one character at a time, the compiler allocates a specific, rigid block of rapid access memory. This block is divided into 2 identical halves.
Hence the name.
Right. Each half is designed to hold exactly n characters, where n is typically the exact size of a standard system disk block, which is often 4096 bytes.
So it grabs data in massive chunks.
Exactly. The compiler issues a single, highly efficient system command that basically says, read the next 4096 characters from the hard drive and dump them entirely into the first half of my buffer.
So it swallows a huge chunk of the text file in one gulp.
Yes. Now, all the scanning and retracting happens locally in RAM, which is millions of times faster than talking to the disk.
And how does it navigate this massive chunk of data?
It uses 2 distinct memory pointers. The first is called the beginning pointer. Its job is to drop an anchor at the exact character where the current lexing begins.
Okay, the anchor.
The second is the forward pointer. The forward pointer is the scout. It is the one rapidly marching ahead, character by character, feeding data into the transition diagram.
So in our +5 example, the beginning pointer is anchored on the plus sign.
Correct.
The forward pointer moves to the plus sign, feeds it to the machine, and the forward pointer moves to the 5, feeds it to the machine.
Right.
The machine hits the asterisk, triggers a retraction, and all that means physically is that the forward pointer steps backward one space, settling back onto the plus sign.
Precisely. It is just basic pointer arithmetic. The string of text trapped between the beginning pointer and the forward pointer is the confirmed lexeme.
And then what?
Once the token is evaluated and shipped to the parser, the beginning pointer snaps forward to catch up with the forward pointer, and they both prepare to scan the next sequence.
And why are there two halves to the buffer? Why not just one massive block?
Oh, it is a brilliant trick for continuous operation. As the forward pointer is rapidly scanning toward the end of the first half of the buffer, the compiler knows it is about to run out of text.
Right, it's hitting a wall.
Without pausing the scan, the system can issue a command in the background to fetch the next 4096 characters from the disk and load them into the second half of the buffer.
Oh, wow.
By the time the forward pointer crosses the boundary, the data is already there waiting for it. They operate in a continuous cycle, leapfrogging each other.
That is incredibly smooth.
Yeah, and if the system ever tries to fill a half and gets fewer than n characters back from the disk, it knows it has reached the end of the file, and it inserts a special EVE or end-of-file character so the lexer knows to terminate cleanly.
It is an incredibly intricate, synchronized dance of memory management, pointer arithmetic, and theoretical mathematics.
It really is beautiful.
But even with the most elegant two-half buffers and the most rigorous Chomsky hierarchies, things are going to break. Because ultimately, this perfect mathematical system has to process languages designed by erratic, illogical human beings.
Very true.
And human language design is full of terrible ideas. Let's look at where lexical analysis fundamentally struggles, starting with how it handles errors.
This is where the pristine theory collides violently with reality. The most critical limitation to understand about a lexical analyzer is that it operates with a strictly localized view of the universe.
It's wearing blinders.
Completely. It can only see the characters immediately surrounding its forward pointer. It has absolutely zero broader context about what the program is trying to achieve. Because of this, the lexer is entirely incapable of catching significant syntax errors.
So if I write a perfectly spelled line of code, but I put it in the completely wrong place, like putting a variable declaration inside a mathematical equation, the lexer doesn't care.
It doesn't even know it is wrong. Let me give you a simpler example. Suppose you're trying to write an if statement, but your finger slips and you type F-I.
Typical typo.
Right. The lexer looks at the letter F and the letter I. It runs that through its patterns. It says it starts with a letter and it's followed by another letter. That perfectly matches the pattern for an identifier.
Oh.
Yeah, it proudly packages up the token id with a pointer to phi and hands it to the parser. It is entirely up to the parser, which has a broader contextual view of the grammar, to look at that token and panic, realizing that an identifier makes absolutely no structural sense in that position.
If the lexer can't catch spelling mistakes or structural errors, what kind of errors can it catch?
Its error detection is basically limited to illegal characters.
Like what?
If you are compiling a standard C program and you randomly insert a bizarre, non-standard Unicode symbol, like a decorative hieroglyph or something,
Right.
the lexer will read that character, look at its transition diagrams, and realize there's not a single arrow leaving state 0 for a hieroglyph.
It just hits a wall.
Exactly. It immediately hits a dead state without producing a lexeme. At that point, it halts and throws a lexical error complaining about an illegal character. But beyond that, it just blindly follows the patterns it was given.
And that blind obedience to patterns leads to some truly nightmarish scenarios, depending on how the programming language itself was designed.
Oh, language design is everything.
The documentation highlights a historical example that is famous among compiler engineers. It involves Fortran, one of the oldest high-level languages.
Oh, Fortran.
If you are listening to this and you've never coded in early Fortran, prepare to be horrified by how difficult it made life for the compiler.
Fortran is the ultimate cautionary tale in language design. The notes explicitly highlight two specific rules in older Fortran specifications that make lexical analysis almost impossibly complex.
Let's hear them.
The first rule: white space is entirely insignificant. Blanks are completely ignored by the compiler. You can put spaces in the dead center of a variable name, and the compiler just pretends they aren't there.
That alone is terrifying.
That gets worse. The second rule: keywords are not reserved.
Not reserved.
No. In modern languages, you cannot name a variable if or while because the system reserves those words for logical operations. In Fortran, you can absolutely use a keyword like do or I as a standard variable name.
Okay, let's look at the 2 lines of code provided in the text to demonstrate why this breaks the machine. Example 1 is a standard loop statement. DO100I equals 10 order 2.
Right.
In Fortran, this means execute a DO loop, using the variable I, looping from the value 10 to the value 2, and use the label 100. So in this context, the word DO is functioning as a strict keyword.
Correct. Now look at example 2. It reads, DO100I equals 100.2. Notice the decimal point at the end instead of a comma.
Okay.
Because Fortran ignores all spaces, the characters DO100I are instantly squashed together by the lexer into a single continuous string, DO100I.
Wow.
And because keywords aren't reserved, this entire string is treated as a single valid identifier. The statement simply means assign the floating point value 100.2 to the variable named DO100I.
Wait. I want to make sure I'm grasping the scale of this problem. In the first example, the letters D and O represent a fundamental keyword that changes the entire control flow of the program.
Right.
In the second example, the exact same letters D and O are just the first two letters of a random variable name. And the lexer, which we established, has no memory and only looks at a few characters at a time, has to figure out which is which.
It is an architectural catastrophe.
It really is.
If the lexer is sitting at the beginning of the line looking at the letters D and O, it cannot possibly make a decision. The only way to resolve the ambiguity is to completely violate the principle of localized scanning.
What does it have to do?
The lexer is forced to execute substantial look-ahead. The forward pointer must scan past the D, past the O, past the spaces, past the 1, the 0, the I, past the equal sign, past the next 1, 0, 0, all the way until it hits either a comma or a decimal point.
It has to buffer practically the entire line of code just to understand the first two letters.
Exactly. If it finally sees a comma in that specific grammatical position, it retracts the pointer all the way back to the O and says, okay, DO is a keyword.
And if it's a decimal?
If it sees a decimal point, it retracts and says, okay, DO100I is a single identifier. It forces a fast, lightweight scanner to perform incredibly heavy, complex, and slow look-ahead operations.
This sounds miserable.
This is exactly why modern languages like Java, C, and Python enforce strict rules about whitespace and explicitly reserve keywords. They made the language slightly more rigid for humans so that the lexical analyzer could run millions of times faster.
But even in modern, well-designed languages, ambiguity still exists naturally. The lexer will often find itself looking at a sequence of characters where multiple different patterns seem to be valid matches simultaneously.
Oh, constantly.
How does a purely mathematical machine resolve a conflict without human intuition? The architecture defines two golden priority rules.
Yes. A machine cannot function without absolute rules for conflict resolution. The first, and by far the most dominant rule, is the longest match rule.
Longest match.
When faced with multiple valid pattern matches, the lexer is hard-coded to always prefer the pattern that consumes the largest number of characters to produce the longest valid lexeme.
The documentation gives a great example. DO versus DOT. Let's say the lexer reads the character D, then the character O. It checks its rules and says, hey, DO is a perfectly valid keyword. I could stop right here.
Right.
But the longest match rule forbids it from stopping. It forces the forward pointer to check the next character. It reads the T. Now the string is DOT. The lexer realizes, wait, DOT matches the pattern for an identifier, and DOT is longer than DO. Therefore, I must discard the keyword match and accept the identifier match.
A much more common example that programmers hit every day involves relational operators. Consider the greater than operator and the greater than or equal to operator.
Oh, yeah.
If the lexer reads a single greater than symbol, that is a perfectly valid token. It could accept it immediately. But the longest match rule forces it to look at the very next character.
Okay.
If the next character is an equal sign, the machine sees that the combined string is a valid pattern, and because it is two characters instead of one, the longer match wins. It returns the greater than or equal to token.
And if it's not an equal sign?
If the next character was a space or a number, the longer match would fail, and it would accept the single greater than token.
That makes perfect sense. Longest match is the supreme law. But what happens if two completely different patterns match the exact same string of characters, resulting in the exact same length?
That is where the second priority rule takes over. The first listed pattern rule.
First listed?
Yes. If the lengths of the competing lexemes are identical, the lexer defaults to whichever pattern was physically listed first in the source code of the lexer's configuration file. The order of the rules dictates the reality of the language.
Where does a length tie actually happen in practice?
It happens constantly with keywords. Think about the keyword while. It is 5 characters long.
Okay.
Now think about the general pattern for an identifier. a letter followed by any combination of letters and numbers.
Right.
The string W, H, I, L, E perfectly matches the identifier pattern, and obviously it perfectly matches the keyword pattern for while. They're both 5 characters. It's an absolute tie.
So whoever programs the lexer has to be incredibly careful. If they list the general identifier rule at the top of the file and they put the keyword rules at the bottom, the lexer will evaluate a string, hit the identifier rule first, and say, match found.
And that's a disaster.
The word while will literally cease to exist as a logical keyword in that compiler. It will just be treated as a standard variable name forever.
Exactly. You must rigorously list all specific keyword patterns physically above the general identifier patterns to ensure the first listed rule prioritizes the keyword.
That seems error-prone.
It is. Writing out complex regular expressions for dozens of individual keywords like if, else, while, for, return, class, and painstakingly managing their order is very prone to human error.
So what's the alternative?
The notes describe this cumbersome method as solution B, but they also outline a solution A, which is a wildly elegant architectural trick that bypasses the problem almost entirely.
I love an elegant trick. How does solution A avoid writing all those keyword patterns?
It relies on the power of the symbol table we discussed earlier. In solution A, the engineer designing the lexer doesn't write any transition diagrams or patterns for keywords at all.
Wait, really? None at all?
None. They write one single, robust, overarching pattern that recognizes any sequence of letters as a standard identifier. The lexer is essentially built to assume that keywords do not exist.
Okay, so every word in the code is initially categorized as an identifier token. How do we get the keywords back?
Before the compiler even begins reading the source code, the system performs a setup phase. It preloads the symbol table.
Tree loads it.
Yes, it manually inserts strings like while, if, and else directly into the database, and it permanently tags their data type as keyword instead of variable.
Oh, that is brilliant.
Isn't it?
So the scanner reads the letters W-H-I-L-E-E. The transition diagram blindly follows the rules and says, yep, that's an identifier. It takes the lexem while and goes to the symbol table to create a new row.
Right.
But when it tries to insert it, the symbol table says, hold on, while is already in here. And look at its tag. It's not an identifier, it's a keyword.
Precisely. The lexer dynamically intercepts the token based on the database lookup. It changes its mind at the last millisecond and outputs the token keyword while instead of the generic ID token.
That is so smart.
This trick drastically reduces the complexity and the sheer number of states required in the transition diagrams, leaning instead on the lightning-fast lookup speed of a hash-based symbol table to differentiate words on the fly.
Okay, we have covered the mathematical theory, we've walked through the memory pointers, we've dissected the edge cases, and we've marveled at the clever database tricks.
We've covered a lot.
Now let's bring it all back to the real world. If I am an ambitious software engineer and I want to actually build one of these lexical analyzers tomorrow, where do I start?
Good question.
The documentation outlines 3 distinct implementation methods, and they represent a fascinating study in software engineering trade-offs.
Choosing how to implement the lexer is one of the most critical decisions a compiler architect will make. The first method is to use automatic generators.
Automatic generators.
Yes. In the Unix ecosystem, the classic tool is called LEX, or its modern open source equivalent, FLEX. These are essentially programs that write programs.
How does it work? Do I just give it a list of words?
You write a very high-level configuration file. You just type out the raw regular expressions, the patterns, and you write tiny snippets of code dictating what to do when a pattern is matched, like return ID token.
Okay.
You feed this configuration file into LEX. LEX reads your patterns, does all the complex set theory math in the background, automatically constructs the transition diagrams, and then physically generates thousands of lines of C code containing the massive sprawling state tables and evaluation loops required to run the machine.
That sounds like a miracle tool. It does all the hard work for you. Why wouldn't every single engineer use an automatic generator?
Well, the immense advantage is rapid development speed. You can prototype and build a fully functional lexer in a matter of hours rather than weeks or months.
Right.
But the cost is significant. Because the generator is a general-purpose tool designed to handle any possible language, the C code it spits out is notoriously bloated and heavily reliant on massive two-dimensional array lookups to navigate the state tables.
Oh, so it's inefficient.
Very. It is not highly optimized for the specific, unique quirks of your particular language. It runs slower. Furthermore, If a subtle bug occurs deep inside the generated state machine, it is nearly impossible for a human engineer to open that generated C file, read the thousands of lines of boilerplate, and figure out what went wrong. It is a black box.
So you trade runtime speed and long-term maintainability for raw development speed.
Yeah.
What is the second method?
The second method is the handwritten approach using a high-level language, or HLL.
Okay, like what?
This means sitting down with a language like C++, IA, Java, Rust, or Go, and manually translating the transition diagrams into code.
That sounds like a lot of work.
It is. The engineer literally writes out the while loops to advance the forward pointer and writes massive nested switch statements to represent the transition arrows moving from state 0 to state 1 to state 2.
That sounds incredibly tedious.
It is extremely manual and takes a significant amount of engineering time. However, the resulting software is a masterpiece of efficiency.
Really?
Yes, because the engineer wrote every line, they can compress the logic, eliminate redundant states, and perfectly tailor the memory management to the specific language they are compiling.
That makes sense.
The final executable is highly compact and blindingly fast. And most importantly, if there is a bug, the engineer understands the code completely and can debug it directly.
And what is the absolute extreme? The third method.
The third method is handwriting the lexical analyzer in a low-level language, which practically means writing it in raw assembly code.
Assembly code.
Yes. This strips away all the comforts of modern programming. You are directly managing the CPU registers, manually allocating bytes of RAM, and writing the literal machine instructions.
Why would anyone subject themselves to that?
For absolute, uncompromising performance. An assembly-written Lexer can squeeze every single microsecond of processing power out of the hardware. It represents maximum efficiency and maximum compactness.
But the downsides.
The disadvantages are severe. Writing complex logic in assembly is brutally difficult, debugging it is a nightmare, and the resulting code is locked to a specific computer architecture. If you write it for an Intel chip, it won't run on an ARM chip without being completely rewritten.
So when you look at the landscape of modern professional compilers, the ones compiling the software we use every day, which path do the engineers usually take?
It is a perfect reflection of software engineering philosophy. If you are building a rapid prototype, an academic project, or a small domain-specific language for internal company use, tools like LEX and FLEX are invaluable.
Right, because the speed is worth it.
Exactly. The minor hit to runtime efficiency is entirely worth the weeks of saved development time. But if you are building a foundational, production-grade tool, like the official compilers for C, Java, or Python, the equation flips.
Because those compilers are run millions of times a day by developers all over the world.
Exactly. If you can optimize the Lexical Analyzer to run just 50 milliseconds faster, and your compiler is executed 10 million times a day globally, you are saving staggering amounts of collective human time and computational energy.
That is wild to think about.
For those foundational compilers, the handwritten approach in a high-level language is the industry standard. Organizations will willingly pay brilliant engineers to spend months painstakingly hand-coding and optimizing the Lexer just to shave off a fraction of a second for the end user.
It is a phenomenal invisible effort that supports the entire digital world.
It really is.
Well, we have covered an incredible amount of ground today. We started by asking how a machine reads human code, and we found our answer in the mechanics of lexical analysis.
A lot of mechanics.
We explored the architectural necessity of separating the lexer from the parser, keeping the hard drive I/O away from the high-level grammar.
And we unpacked the core trinity: the abstract token categories, the rigid mathematical pattern rules, and the concrete physical lexeme strings.
We waded into the deep waters of formal language theory, establishing that lexers are strictly constrained to Type 3 regular languages.
We saw how the lack of a memory stack makes them incredibly fast, relying on finite state automata instead of the heavy pushdown automata used by the parser.
And we broke down syntax analysis, showing how the parser builds that beautiful parse tree out of the tokens. We visualized the practical transition diagrams, navigating through accepting states, hitting dead states, and utilizing that crucial retraction asterisk to manage look-ahead ambiguity.
And we look at the brilliant engineering of the 2-half memory buffer that keeps the disk drives from bottlenecking the system.
We saw the horrors of Fortran forcing massive look-aheads and how the longest match and first listed priority rules keep the machine from breaking down.
And finally, we saw the reality of building these systems, weighing the speed of automated generators against the bespoke performance of handwritten code.
You know, this deeply complex, hyper-optimized process we just spent an hour dissecting is happening invisibly, millions of times a second on the devices around us.
It's everywhere.
Every time a web browser renders a script, every time an app updates, a lexical analyzer is silently, ruthlessly translating human logic into mathematically pure structures.
It is a profound mechanical process, and it leaves me with a final thought, something not explicitly written in the math, but echoing through everything we have discussed.
Oh, let's hear it.
Lexical analysis is, by its very design, a process of systematic erasure.
Erasure.
Yes, it is entirely devoid of context. Its fundamental purpose is to strip away the formatting, to permanently delete the comments, and to completely ignore the programmer's human intent.
That's kind of sad.
It takes the expressive, narrative nature of writing code and boils it down to raw, categorized, cold mathematical coordinates.
The machine doesn't care about the poetry of how you structured your logic. It doesn't care about the clever joke you left in the comments. It only cares that you adhered to the pattern.
Exactly. The first step of a machine understanding a human is the machine stripping away the humanity.
Wow.
So the next time you write an elegant, heavily commented, beautifully indented piece of code, a piece of work you are genuinely proud of, take a moment to think about the Lexical Analyzer.
Yeah.
In the first millisecond of compilation, it will shred all your poetry into a stream of integers and pointers. It forces you to wonder, outside the realm of computer science, how much of human communication, nuance, and genuine intent is inevitably lost the moment we try to force it into a formalized, perfect system?
That is a brilliant question to leave on, a stark reminder that building a perfect system always requires stripping away a little bit of the human element. Keep diving deep, keep questioning the invisible systems that run the world around you, and we will catch you on the next one.